All right, welcome back. Today we're jumping into a real classic from the legendary Irodov physics textbook. We're going to tackle a two-dimensional collision problem, and I know these can be a real headache sometimes. So if you've ever gotten tangled up in the vectors and the components, this explainer is definitely for you. Let's get right into it. So the setup is super straightforward. Picture this. We've got two particles. One of them is zipping along, and the other one is just sitting there, totally stationary. And then, bam, they collide and scatter off in completely different directions. But we're not just watching, we're investigating. Think of us as detectives at the scene of a particle collision. And the big question we have to answer is, was it a clean hit? You know, a perfectly elastic collision where all the kinetic energy is conserved? Or was it inelastic, meaning some of that energy got lost in the impact? To solve this little mystery, the first thing we've got to do is gather all the evidence. So let's lay out all the facts of the case, straight from the problem itself. So here's the rundown. A small particle, mass m, smacks into a stationary particle, mass m. We get a play-by-play of what happens next. The little particle m shoots off at a perfect 90-degree angle from where it started. Meanwhile, the big particle m recoils at a 30-degree angle. And here's a critical clue. The mass ratio, m over m, is exactly 5. Our mission is to figure out how the system's kinetic energy changed, and by what percentage. That's the key to cracking this whole thing. Okay, let's get all our facts straight. Before the smash-up, only particle m is moving. We'll just call it speed v. After they hit, we know their exact directions, and we know that particle m is a whopping 5 times heavier than particle m. These are all the puzzle pieces we have to work with. So we've got our clues. Now, what's the first tool we pull out of our physics toolbox? Well, for any collision problem, and I mean any, your go-to, your number one most powerful tool is always the law of conservation of momentum. This law is a fundamental rule of the universe. It's non-negotiable. It just means that the total amount of oomph in our two-particle system before they hit has to be exactly the same as the total oomph after they fly apart. No momentum gets created, none gets destroyed. It just gets passed around between the particles. Okay, listen up, because this right here is the number one trap. This is where everyone messes up these problems. You absolutely cannot forget that momentum is a vector. It's not just about how much momentum there is, it's also about which way it's pointing. If you just add the numbers and ignore the directions, you are guaranteed to get the wrong answer. So what's the secret to handling vectors? We use this foolproof 3-step strategy. We draw it out so we can see what's happening. And then, and this is the magic trick, we break this one complicated 2D problem into 2 super easy 1D problems. We'll look at all the horizontal motion separately from all the vertical motion. All right, time to put our plan into action. The first thing we'll do is set up our x and y axes. And let's make our lives easy, right? We're going to line up the x-axis with the original path of our little particle m. That way, all of the starting momentum is pointed perfectly in the x direction. Let's start with the y-axis because it's the easy one. Before the collision, was anything moving up or down? Nope. So the total vertical momentum was a big fat 0. And because momentum has to be conserved, that means after the collision, the total vertical momentum still has to be 0. Any upward motion from one particle has to be perfectly balanced by the downward motion of the other. And this equation right here is just putting that idea into math. The upward momentum from particle m has to be perfectly canceled out by the downward piece of momentum from particle m. It's the only way the two can add up to 0. Now let's move over to the x-axis. This is where all the action was happening at the start. The entire momentum of the whole system was just mv, all pointed in the x direction. So after the crash, when we add up all the final pieces of momentum in the x direction, they have to equal that same initial amount. So let's write that out as an equation. On the left side, we have our initial momentum, m times v. On the right side, well, particle m shot straight up, so it has 0 forward momentum now. That means all of the final forward momentum in the system has to come from particle m. And that piece is m times v times the cosine of 30 degrees. And would you look at that? We've got 2 equations from our 2 axes and 2 things we don't know. The final speeds, v prime and v prime. This is just algebra. We can totally solve this system. And check this out. We can figure out what both final speeds are just in terms of the initial speed, v. That is going to be incredibly useful in just a second. Okay, deep breath. We did the hard vector part. We used conservation of momentum to figure out how fast everything's moving after the collision. Now we can finally go back to our main question and deliver the verdict. What happened to the kinetic energy? Let's do a simple before and after comparison. Initially, all the kinetic energy in the entire system was tied up in that one little moving particle, m. That's our initial energy, k sub I. Afterwards, they're both moving, so the final kinetic energy, k sub f, is the sum of their individual energies. The million-dollar question is, are these two numbers, k sub I and k sub f, the same? And here it is, the big reveal. We take those expressions for the final speeds that we just found, we plug them into our formula for the final kinetic energy, we do a little bit of algebra, and we get this stunningly simple answer. The final kinetic energy is not the same as the initial. In fact, it's only 3/5 of what we started with. So what does that mean in plain English? It means we lost 40% of our kinetic energy. 40%. A huge chunk of the energy of motion just vanished during the collision. Our investigation is complete. The verdict is in. But hold on a second. What does that actually mean? We know from day one of physics class that energy can't just be created or destroyed. So if 40% of the kinetic energy is gone, where did it go? This, my friends, is the classic sign of what we call an inelastic collision. That lost energy didn't really disappear. It just changed its costume. It transformed into other forms of energy. Maybe it warmed the particles up as heat, maybe it created the thwack sound of them hitting, or maybe it even dented one of the particles permanently. That conversion is what an inelastic collision is all about. So let's recap your new go-to toolkit for any 2D collision problem. First, draw the picture, always. Second, decompose it into x and y components. Remember, momentum is a vector. Third, calculate your unknowns, and finally, use those results to classify the collision. Was it elastic or was it inelastic? It's a method that works every single time. And I'll leave you with one last thing to chew on. We proved this collision was inelastic, but what if we wanted it to be perfectly elastic? If we insisted on keeping these exact same angles after the collision, what would have to change to make sure absolutely no energy was lost? Would the mass ratio have to be different? That's the kind of question that moves you from just solving problems to really understanding the physics. Give it some thought. Thanks for joining me.